A fabrication bay. A pipe spool on stands, waiting for a joint. Everything that will ever hold pressure in this line depends on what happens in the next few minutes. Look closely at the prepared edges. A bevel. A root face. A gap set with care. Now the arc strikes. Metal melts, a pool forms, and the bead runs along the joint, ripple by ripple. Heat floods outward from the fusion line, the heat-affected zone, then cools, and the steel changes color as it goes. This is not a coating. It is a small casting fused into the pressure boundary. We will follow that weld from preparation through to acceptance, joints and grooves, processes and filler, an educational P-number example, heat treatment, the stresses welding leaves behind, and the inspection that proves the joint. Training framing never a substitute for the code of record on your job. It starts at the bench, before any arc. The edges are prepared, the parts are aligned, the root gap is set, and tack welds hold the fit up. Get this wrong and no welder can rescue it. How the parts meet defines the joint. A butt joint brings two edges together in the same plane, the pipe girth weld, the vessel seam. A fillet joins members at roughly a right angle with a triangular deposit. Corner, lap and edge joints cover the rest. Now watch the groove change shape. Square, for thin material with a controlled gap. Single V, opening the face for thicker sections. A single bevel, where only one member is prepared. U and J grooves, curved to cut the volume of filler on heavy walls. And double-sided preparations, balancing shrinkage when you can reach both faces. 3 details govern the root: the bevel angle, the root face, and the gap. Weld symbols carry that intent from the drawing to the fitter. Different processes lay metal in different ways. Shielded metal arc stick burns a covered electrode and leaves a slag blanket that must be chipped and cleaned between passes. Feel flexible and forgiving of position. Gas tungsten arc holds a non-consumable tungsten and dabs filler into the pool by hand. Slow, clean, and the usual choice for a critical root in pipe. Gas metal arc feeds a solid wire continuously under shielding gas, for high deposition in the shop. Flux cord feeds a tubular wire and pushes deposition rate higher again. The filler must match the base metal for strength, chemistry and service, not simply share a name on a warehouse tag. Take E7018 as an educational example of a covered electrode designation. 70 is a minimum tensile strength class, in thousands of pounds per square inch. The 1 indicates all position capability in that system. The 8 points to a low hydrogen, iron powder coating family. Always confirm the exact classification against the filler specification and the approved procedure. And remember weldability: the more hardenable the steel, the greater the cold cracking risk in the heat-affected zone, which is why preheat and low hydrogen practice exist. Now the paperwork problem. A plant holds dozens of base metal grades, and qualifying a separate welding procedure for every one of them would be impossible. ASME Section 9 solves this by grouping base metals that behave alike for welding into P numbers. Watch the population filter down. Out go the stainless grades, the nickel alloys, the aluminium. What collects together is the carbon steel family, the P number 1 concept. Here is an illustrative example. You need a procedure for carbon steel process piping in that family. You weld and test a coupon on a representative P number 1 base metal, and the results become a procedure qualification record, the PQR. That single qualified record can then support welding procedure specifications for other permitted P number 1 combinations, within the thickness, process and essential variable limits of Section 9. 2 companion groupings help: F numbers group filler metals for qualification, and A numbers describe the deposited weld metal chemistry. This is training language, not a code interpretation. Verify the addition, the essential variables, and the owner's specification before you claim anything is qualified. Heat is a controlled variable, before, during and after welding. Preheat raises the parent metal before the arc ever strikes. It slows the cooling rate, gives hydrogen time to escape, and reduces the risk of cracking in hardenable steels. Interpass temperature is the ceiling you hold between passes, protecting toughness and microstructure. Then, when the code or the specification calls for it, comes post-weld heat treatment. The joint is heated under control, in a furnace, or locally under blankets held at temperature to relax residual stress and temper the hard zones, then cooled at a controlled rate. Watch the curve. A ramp, a soak, a controlled cool. Distinguish this from a hydrogen bakeout, which is a lower temperature hold intended to diffuse hydrogen out of the weldment. A bakeout is not stress relief, and it never replaces a required post-weld heat treatment cycle. Temperatures, ramp rates, and hold times belong to the applicable construction code, material group and thickness. Treat anything you see in a classroom as illustrative only. Watch what happens as the weld cools. The molten metal solidifies and then contracts, but the surrounding steel will not let it. The plate pulls in. The joint closes on itself and rotates angular distortion, and the whole assembly shrinks along the weld. When it finally stops moving, the metal is locked in a fight with itself. Tension sits in the weld and heat affected zone. Compression balances it farther out. No external load is applied, and yet stress is present, a self-equilibrating residual field. Now look at the toe, where the weld face meets the plate. Service stress flowing through the joint crowds into that change of section. Add pressure, thermal restraint and cyclic operation on top of the residual tension, and this is precisely where fatigue cracks begin. That is why joint profile, welding sequence, and post-weld heat treatment are engineering decisions, not cosmetic ones. Finally, the joint has to be proven. Visual examination comes first and never stops: fit up, profile, undercut, surface condition, pass by pass. Liquid penetrant is drawn into anything open to the surface, and the developer pulls it back out as a visible indication. Magnetic particle testing magnetizes ferromagnetic steel, and particles gather where a surface or near-surface crack disturbs the field. Both find surface flaws. Neither tells you what is happening inside the wall. For that you need volumetric methods. An ultrasonic probe sweeps along the weld and sends a beam into the joint. When it meets lack of fusion or a crack, an echo returns, and the flaw's depth comes with it. Radiography exposes the volume through the thickness and images what lies within. Match the method to the defect you are hunting, because a technique that cannot find your flaw earns you nothing. And behind all of it stands the documentation. The welding procedure specification says how to weld. The procedure qualification record proves that procedure produces sound properties. Welder qualification proves the person can execute it. The inspector's checkpoints run from fit up and preheat, through parameters, to final examination and closeout. The finished joint carries pressure, temperature and time, quietly, for years. It earns the trust from the whole chain, not one step. Prepare and fit the joint correctly. Match filler and process to the base metal and the service. Use P-number grouping thoughtfully, and verify against Section 9. Control preheat, interpass and post-weld heat treatment. Respect the residual stress and distortion you have built in. Then inspect with methods that can actually find the defect you fear, and keep the documentation aligned with what was really welded. That is how a weld stops being a risk and becomes a barrier. JAR ASA Consultation Services. Integrity, inspection, reliability.